So our final topic is the Laplace transform of derivatives. Now, Laplace transform, it's so powerful because it allows us to solve differential equations. And since we are going to look at systems modeling, we are going to model system in terms of their dynamic, and it will be easier and simpler if we use the Laplace transform to look at this dynamic so that we are able to see how the response of the system is, and if we are going to design a controller, what type of controller are we going to design, how do we want this system to behave, to settle, to respond, etc. Now, before we go further, we are going to look at some properties, just basic simple properties of derivatives that or that is going to help us simplify our equations. The first one is if we have a Laplace of x of t, which is in the time domain, the Laplace of this is x of s. And if we have a first derivative, so let's say this is x dot, then the Laplace of the first derivative is s x of s minus x naught. Now this x naught is an initial condition, because whenever you are looking at dynamic systems, and if you have a first derivative, you're gonna have one initial conditions. If you have second derivatives, you're going to have two initial conditions. Third derivative, three initial conditions. Most of the time, if the initial conditions are not given, you just assume that the initial condition is 0. So x naught is the initial condition. If you have x double dot, then the Laplace transform is, we're going to have s squared times x of s minus the first derivative initial condition, which is s x naught of the Laplace transform, and x dot. The next one is the third derivative. If you have x dot 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 is equal to s to the third x of s minus your first Laplace initial condition, which is s squared x naught minus another initial condition, s times x dot x naught minus x dot dot initial condition. So these properties are really crucial in solving derivatives using the Laplace transform. Now let us look at our first example. Let's say we have, let's say the question says, okay, which Laplace model represent the following ODE? So we just want the Laplace model that represent this ODE. Hence we assume that the initial condition is 0. So and the ODE is 3 dx dt plus 6x is equal to 9. So we know the Laplace transform of the first derivative. So Laplace transform of dx dt is equal to s x of s minus x naught. And we take the Laplace transform of we take our 3 outside, dx dt plus 6 times the Laplace transform x of t, which is equal to 9 times the Laplace transform of 1. So first we are going to work out the Laplace transform of this, then we work out the Laplace transform of this, and we work out the Laplace transform of this respectively. So we have 3 times s x of s minus x naught, which is your initial condition, assuming it's not given, but I'm going to carry it so that next time if it's given you'll see where you are going to substitute it if need be, plus 6 x of s, which is equal to 9 times Laplace of 1 is 1 over s. From here we'll just clean up our equations. So we have 3s x of s minus 3x naught plus 6 x of s is equal to 9 over s. And we are going to factor out our x of s, which is common, and we are going to have x of s on the outside, then we have 3s plus 6, which is equal to 9 over s. Then we can take this on the other side, plus 3x naught. And we want, because we want this, we want the model that represents the ODE. So what we are going to have is x of s is equal to 9 over s plus 3x naught over 3s plus 6. Okay? So this is the model that represents the ODE. And if we assume that the initial condition is 0, assuming that the initial condition is 0, then this will just be 9 over s over 3s plus 6. Let me find another example so that you are comfortable with this. What if we have 2 dx dt minus 5x is equal to 4u. Again, just write it in a simple way. So you have 2, take the Laplace transform of the first derivative, which is dx dt, minus 5 times the Laplace of x of t is equal to 4 times the Laplace transform of u of t. Okay? Again, then you write 2 times, we know the Laplace transform of dx dt is s x of s minus x naught minus 5, take the Laplace transform of x of t is just x of s, which is equal to 4. The Laplace transform of u of t is going to be u of s, u of s. And of course, since the initial condition is not given, so I'm going to take that to 0, so that we have, and I'm going to factor out the x of s, So we have x of s times you have 2s minus 5, which is equal to 4 u of s. So x of s is equal to 4 over 2s minus 5 times u of s. Let me try and find an example with initial condition. Let's say you have a third derivative, dt to the third, minus a second derivative, dt squared, is equal to 0, and your initial condition. As I said, if you have a third derivative, you need to have 3 initial conditions. So you have the first initial condition, x naught, and let's assume that this initial condition is the same as the second initial condition, which is the same as the other initial condition, which is equal to 3. Now we need to find, we are going to work this out. We want the Laplace transform of a third derivative, dt to the third, minus the Laplace transform of a second derivative, which is equal to 0. So the first one is s to the third x of s minus the first initial condition, which is s squared x naught minus s x naught x dot x naught minus x double dot x naught minus the second derivative, which is s squared x of s minus s x naught minus x dot x naught. This is all equal to 0. Next, we need to substitute the initial conditions. Again, we have s to the third x of s minus the first initial condition, which is x naught. So you have s squared x naught is 3. So let me just write it. I want to write the initial condition in a different color. So it was given as 3 minus s x dot naught, again is 3. Just gonna put it here. Minus x double dot, which is also 3, minus s squared x of s minus, again, x naught is 3, so we have 3s minus x dot, which is also 3, which is equal to 0. As you can see, a third derivative has 3 initial conditions. A second derivative has 2 initial conditions. A 4 order will have 4 initial conditions, and so on and so on. So now we are going to rewrite the entire equation so that we can simplify. So we have s to the third x of s minus 3s squared minus 3s minus 3 minus s squared x of s. Minus times minus is plus, so we're gonna have plus 3s plus 3 is equal to 0. So now we are going to have some cancellation. This and this cancel out, and this and this cancel out as well. So we are going to simplify. So we're going to have x of s. So we have s to the third minus s squared minus 3s squared is equal to 0. Then we can take the 3s squared on the other side. If we do that, let me just rewrite it here. So we're going to have x of s times s to the third minus s squared is equal to 3s squared. Therefore, you're going to have x of s is equal to 3s squared over s to the third minus s squared. And you can also simplify this further, and because remember you have s squared and s squared will go, so you're going to have 1 here left, and s squared and another s to the third will leave you with 1s there. So this implies that you're going to have a 3 over s minus 1.